Hi there and welcome back to Triplicate and part 11 of the digital synthesis tutorial and the final part. I could go on pretty much forever and talk about things like FM and digital modelling, but I'm sort of largely going to restrict this series to what I implemented in the Dark Star and Elevator. And I shall probably start a new series, and we will look together at other forms of synthesis and have a play around with them. Having said that, this video is going to be a bit different in that we're going to look at a couple of things that I didn't implement in the Elevator or the Dark Star, but wish I probably had. Firstly, we're going to look at warmth. I always complained those two machines, as people said they were good, but the filter was cold. So we're going to take a look at what makes the filter warm and see if we can make our filter warm. And secondly, we have two filter elements, and currently in accordance with synthesizer tradition, I suppose, we've got 12 and 24 dB low pass filters, and that's it. So we're going to look if we can configure those two elements somehow in some different way and produce something interesting and unusual. So without further ado, let's get on and look at filter warmth. Okay, so I did a little digging on the old internet, and one of the things I came up with this Ask Audio article, Synthesis Essentials, Know Your Filters, and it gives basics on what filters look like, and we get down to here and the transistor ladder filter, and this image here is a patent, Bob Moog's patent of his voltage controlled filter. So I thought, wow, well, that sounds warm enough, surely. I mean, that is the classic analog synthesizer filter. So if we can get some ideas from that, then we're surely on the right track. So at this point, I'd like to go off on a little tangent, a little aside. And say at no point are we going to try and digitally recreate a Moog filter. I am sort of pretty much against trying to recreate old technology, and having worked on the Novation drum station trying to recreate a TR-808 and a TR-9 Roland drum machines, we found that we put more and more effort getting nearer and nearer, and for all that effort the best you can ever do is the same, just a copy of something that exists in the past. So I would much rather sort of pinch some ideas from the past and try and use them and adapt them and think of some new ideas to add to them and make something exciting for the future. So that's just a bit of a rant, a bit of a getting up on my high horse. So now we'll return to looking at filter warmth. Now, I don't want to spend a lot of time getting into analysing how the ladder filter works, but the key fact in its operation is that it makes use of the diode characteristics of the base emitter junctions of all these transistors. So we are going to look at a much simpler version of this filter based around a diode. Okay, so instead of a resonant low pass filter of 24 or 12 or whatever dB cutoff, we are going to consider a high pass filter of 6 dB per octave cutoff, i.e. Okay, now the cut-off frequency of the filter depends on the capacitance and the resistance, but resistance is a lot easier to vary than capacitance, and most of them we would use a pot to vary the cut-off frequency of our filter. However, we want to control our filter via a control voltage. So how do we go about doing that? Well, we can very simply use a diode, and that works like this. We still have our input going into our capacitor, but that goes into a diode, and that diode is forward biased by a DC voltage, and we are putting an inductor here, so there is no AC path between here and the DC bias voltage. So the voltage here will be the DC bias voltage plus the input voltage through that capacitor. And at the bottom here we want to measure the current going through the diode. So we're going to measure that with a small resistor and a capacitor to get rid of the DC component from the bias. Now I do hasten to add and stress at this point that this is in no way intended to be any sort of practical filter design. We're just trying to get a handle on what is going on. So we are going to assume that this resistor is very small, so it has no effect on the voltage at the bottom of the diode, so that's effectively zero. Ground, that's ground. Excuse my drawing. So let us consider the characteristic of this diode. So here I have a diode characteristic which is essentially exponential. This is the voltage across the diode and this is the current through the diode. So what happens is we are picking a spot on this curve using our V bias voltage, and we are assuming that the voltage from the input through the capacitor is small compared to the V bias voltage. So let us consider two V bias points. So we've got V bias here and V bias here. Right, I need a thinner pen and I need a ruler. So, as I said, the signal voltage we are assuming is small compared to the bias voltage. So, in each case, our signal voltage varies from there to there, and I should have used a roller to draw this bias voltage point. And similarly for our small bias, the signal voltage is from there to there. So let us look at the current variation we get. I'm drawing this by eye. This is not going to be totally accurate. So that is the variation in the diode current, hence the output of our filter for the big bias value. And for the little bias value. And aha, light bulb moment. You can see for the big bias value the variation in current for the signal voltage is large, and for the small bias value the variation in output current for the voltage, input voltage variation is small. Now over our little signal range we're assuming our diode is behaving like a resistor. So R equals V over I. So for this bias voltage we've got the same voltage, signal voltage in both cases. In this case I is large for our bias voltage, so R is small, and in this case the change in I is small for our fixed change in voltage, so R is large. So we are using our bias voltage to change the value of resistance. So that is like having a voltage controlled version of that resistor. So our filter cutoff will change with our bias voltage, and we have a voltage controlled filter. And in addition, because this curve is exponential, we can arrange it so our filter cutoff frequency changes at 1 octave per volt of our bias, which is what we want. So we are using this system to make a voltage controlled resistor in effect. But a resistor, if we plot just over our little, we'll take this one, over our little signal range, a resistor is linear. Now I'll get the ruler out. So that's current and voltage. Our resistor is linear. Ohm's law and all that. The first thing they teach you in electronics, Ohm's law. But this, you can see, is a curve. Something like that. In fact, I'm going to go over that with the Sharpie, the big pen. So, although we have a voltage controlled resistor, it is non-linear. And that non-linearity will cause harmonic distortion. Now, basically that means if you put a sine wave into something that causes harmonic distortion, you'll get harmonics of the sine wave out and a more complex spectrum. And harmonic distortion, well, amplifier designs talk about minimizing harmonic distortion, which again is caused by non-linearities in the amplification. And at the other end, fuzz boxes clip the top and bottom and cause huge harmonic distortion, and guitar amplifiers are somewhere in here, somewhere in between. But that harmonic distortion is what's making our filter seem warm. It's just generating subtle extra tones harmonically related to the input to the filter, which sort of beefs the sound up in crucial areas of the spectrum. So we need to put some non-linearity, like that, somewhere in our filter. And another little aside, from an engineering point of view, you would look at that level of non-linearity and think, oh no, we can't use that, it's unpredictable, it would colour the sound, it it would be all over the place. But from a musical point of view, I guess Bob Moog just built it and found it sounded great, and then yeah, we'll go with that. So from a musical point of view, just always don't worry about the finer points of engineering. Just go for it. Unfortunately, with digital sound, if you do that, you can end up with a horrible digital noise and distortion, which doesn't sound good. Let's give up this digital stuff and get the soldering iron out and build analog stuff, eh? Okay, so I've drawn a little schematic of how our filter works here. Just a quick word of explanation. These two guys are integrators. So that is, you put a constant voltage in here, the voltage here will ramp up steadily, theoretically forever. And the upshot of using this system is that if we're not careful what we do, this can just shoot off to the rail and sit there in electronics and in an integer environment, in a floating point environment. It just goes up to well, I suppose the maximum that floating point will, maximum number floating point will handle. Anyway, the upshot of this is we have to be pretty careful what we do. So I thought, well, why not just put our non-linearity at the input here? Okay, so let's say we're putting a ramp wave in our sawtooth. So we'll try our simplest non-linearity. We'll just clip it, which gives us a waveform like that. But that's not dissimilar to the waveforms we can get out of our oscillator anyway, so we're not really gaining anything. We're just slightly altering the spectrum that's going in. And I tried this, and the result is not that different to what we have to start with. Now I then got to thinking, say, well, we want to actually add some frequencies in that aren't in the harmonic spectrum of our waveform. So here is our waveform, and we are using a resonant filter on that, so we are actually then getting something like that. But if you actually look at that, for a ramp waveform, if the resonance is reasonably high, we'll get and this is like this. If you expand it out, looks like that, and the frequency that this is the resonance, the frequency of the filter resonance. So if we could actually distort this, then we would be adding harmonics to our waveform that weren't in our original waveform, that were related to the resonant frequency, not the waveform frequency. So I think this is actually what we're trying to do. So what I ended up doing was putting our non-linearity in here at this point, at the high pass, because the high pass, because our waveform, our sawtooth and square wave, or a combination of the both waveforms, have a spectrum which drops off with frequency. So the high pass is the point that has the most of the resonance, the frequency of the resonance in, and the least of the frequency of the input in. So let us look at some code and see what I actually did. Okay, so here's our filter. So it calculates the high pass from the input, the low pass and the damping, as it always has. And here is the new bit. We add a filter warm function, which modifies the high pass according to the value of warmth, which is just a parameter, an amount of warmth we want in. So this is the integrator to give us the bandpass, and this is the integrator to give us the low pass. So we need to look at this filter warm function. Now it's just the way I developed it. This sort of warmth is applied around a value of 1, whereas the input to the filter can be quite a big number, so there's a scale value, and that scale value is constant for 12 dB for octave and for 24 dB for per octave filter. It depends on the resonance value, and that was just something I found out empirically, and the function that does it is there at the bottom. So our nonlinearity consists of taking the value, the input, which is val, and adding to it a sine wave, and that has the effect you can see here. So the blue line is just a simple 1-to-1 transfer, and the red line is that with this sine wave added to make it non-linear. So if we try the exponential non-linearity, we concluded that was happening in the Moog filter. Because we're using integrators, the output will rush off to infinity. So the non-linearity has to be, well, kind of linear, if you see what I mean. So in the grand scheme of things, the filter will keep working. Okay, so how does this sound? Okay, so I was using 2 little sequences to evaluate what I was doing. So we have a little bass figure, which I'll play for you with no warmth on it at all. So that's got a 24 dB per octave filter and quite a lot of resonance on it. So now if I find the warmed up version of that, so the warmth increases with time. So here it's 0, and here somewhere it gets up to about 127. So we should hear the timbre changing as the sound file plays. So here we go. Okay, I don't know about warm, it sort of sounds rather harsh and aggressive. Not necessarily a bad sound, but okay. So I've also generated a little sort of arpeggiated sequence with a 12 dB per octave filter. So this is with no warmth on it at all. And here it is with the warmth algorithm acting on it. Okay. The dog going 10 to the dozen in the background. So there we go again. Again, not particularly warm, and it adds a sort of harshness to the sound, which might be a good effect, but not perhaps what I'd originally aimed for. So as I said at the start of this video, this is more an investigation into how we might make the filter warm than a tutorial telling you what I've done already that worked. And I guess I set off sort of thinking, hoping that I could have a control that would be cold and clinical at one end, something like a classic Moog in the middle, and something like a TB303 squelch at the end. And as you can hear from the sound files, I haven't exactly achieved that. Though the results are interesting. And to develop it any further, well, to develop it as far as I have the sequences are little text files, and all the parameters are typed into these text files, so it's very tedious to modify the text file, maybe recompile the code, run it through, load the sound files, and what does that sound like? Maybe if I modify the text file. It's not very musical. It needs to be set up so everything is on a knob and can actually play some notes in and feel what it's like as an instrument. So on that basis I shall return to it, but I shall return to it when I have the mean green pretty much up and running, so I can use that as a test bed and really musically test what I've got. And I also might do some more theoretical investigations into what is going to produce the result we want. And I had originally intended to have this video as the filter warmth and the filter configuration, the parallel filter configuration, but the video's sort of getting a bit long and I've taken ages to get to as far as I've got on the filter warmth. So I'm actually going to wrap it up here, and this will not be the last video. There will be a filter enhancements part 2 video, which will be the filter configuration, specifically the parallel filter configuration. And as ever, in the description you'll find links where you can download the .wav files that I generated making this video, so you can listen to them as they're supposed to be without YouTube's dreadful compression. And also the code files will be available there if you want to actually look at the code I've developed. So for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.